Hi, everyone. Very pleased to introduce our speaker, Hongseok Namkoong. He's an assistant professor in the Decision Risk and Operations Division at Columbia Business School. His research interests lie at the interface of machine learning operations research and statistics, with a particular emphasis on developing reliable machine learning methods for decision-making problems. He's a recipient of several awards and fellowships, including Best Paper Awards at NeurIPS and ICML, and the Best Student Paper Award from Inform's Applied Probability Society. He received his PhD from Stanford University, where he was advised by John Ducci and Peter Glynn, and he worked as a research scientist at Facebook Core Data Science before joining Columbia. Today, he's going to talk about reliable machine learning. Please welcome Hongseok.
Thanks, Jimmy. Thanks for the introduction. I'm going to today talk about a concept called distributional robustness. And I'll demonstrate how it allows us to learn models that can perform uniformly well across different subpopulations. So as all of us probably know, these large-scale machine learning models with the right inductive biases built in, they've been driving rapid progress in computer vision and natural language processing. And for all of these landmark successes, we've seen papers and news articles claiming that we've now achieved human-level performance on various tasks. But unfortunately, these average case high performances, they don't actually translate uniformly to the entire population. So these standard models that are trained to do well on average, they actually perform quite poorly on certain subpopulations, such as underrepresented demographic groups and tail inputs. So recently, Amazon scrapped its plans to automate parts of their hiring process because they realized that the models that they were developing were discriminating against women and rejecting candidates based on keywords like women's college in their CVs. So I'm going to begin by discussing a few challenges that we're currently facing in ML right now. So the first challenge that I'm going to discuss is that even the state-of-the-art machine learning models, they're very sensitive to small perturbations to the data distribution. And this is the case even in the most successful applications. So recently, a group of authors from Berkeley, they made a new test set for ImageNet, which is, of course, the workhorse data set that's been driving the bulk of recent advances in computer vision. So the initial goal for these authors was to see to what extent the recent deep learning techniques had overfit to the original ImageNet test set. But the results they found turned out to be rather surprising. So these authors, they tried to follow essentially identical procedures to replicate the data filtering process on Mechanical Turk used by the original ImageNet team led by Fei-Fei Li. So on the x-axis here, we have performance on the original ImageNet test set, and the y-axis is the new ImageNet test set that they made. And here they implemented a whole bunch of different methods. These are kernel methods and random features. I think this is AlexNet. And we have a VGG here, ResNet, YGresNet, Autocomplete, EfficientNet, and so on. Okay. So what we see here, the red line is simply a linear fit through all of these blue points, and the black dotted line is y equals to x, perfect generalization. So in this plot, what we see is that overfitting actually wasn't the problem, right? Gains on the original test set, it leads to even bigger gains on the new test set. But what we do see is a universal accuracy drop of around 11 to 14% for all of these models. And this is despite the fact that these authors had tried to exactly replicate the previous test set generation process. So what we observe here is that there was a small shift in the data generating scheme. And these modern learning methods, they're quite sensitive to even small distribution shifts. And these types of phenomena have been observed in many other data sets and tasks spanning across computer vision and natural language processing. Now, the second challenge that I'm going to talk about today is that the data that we observe is it's often very long-tailed. And this is true throughout natural and social sciences, as well as internal applications. So for example, at Google, a constant fraction of queries, I heard that are new each day as of around 8 to 9 years ago. And you can see this concretely in this plot of queries on a public data set released by Microsoft Bing. So in this somewhat abstract search engine example, on common queries like, say, the Beatles, there's really no learning involved because lots of people search for this every day. But then for rare queries like, say, Namkoong, no one knows who that is. And this is really where you have to be smart and extrapolate. And according to a Bing engineer, this is really where Bing suffers compared to Google. So here it's really these tail inputs that determine the quality of the service. And of course, this is the case in many, many other applications. All right, the final challenge that I'm going to discuss is that the data sets that we use, the very infrastructure that our models build on, they inherit the socioeconomic and the political power structures that we see in society. So these data sets, they tend to be biased and they severely lack diversity. So for example, it's well known that clinical trials for new drugs are heavily centered around Caucasian groups. So as an example of this, out of more than 10,000 cancer clinical trials funded by the National Cancer Institute, less than 2% of them focus on racial minorities, and less than 5% of the participants were non-white. And in computer vision, the majority of the images that we use to train deep nets with, they're collected in either North America or Western Europe, showing a severe lack of geodiversity. Of course, these types of biases have been observed in a number of different applications, as many of you already know, some of which are listed here. Now, this bias is, of course, something that should really be addressed at every stage of the development pipeline, from data collection to deployment. And things like, say, structural racism, it affects all aspects of this pipeline, and we as a community need to think hard about how to address these issues. But one place where this problem is propagated and exacerbated is the learning algorithm, and this is what I'm going to focus on today. So despite these heterogeneous subpopulations, long-tail data, and underrepresentation biases, the standard machine learning paradigm, it only trains models to do well on average. And this is often what leads models to perform quite poorly on certain tail subpopulations. So let me begin by just setting up some notation that I'm going to be using throughout the talk today. And please feel free to interrupt me if anything's not clear. So I'm going to use L to denote my loss or the objective that I want to minimize. And I'm going to denote by theta the parameters of the model that I want to learn from the data. And Z here is going to denote my random data, which is going to be drawn from the underlying data generating distribution P observation. Okay? So think of Z as a tuple of the feature vector and the label in a typical prediction setting. So then the canonical supervised learning regime, it aims to learn models data that minimizes the expected loss under the data generating distribution. Okay? And this general loss minimization framework, it's abstract enough to cover virtually all supervised learning problems. So from regression to classification losses using simple linear models to over-parameterized models like deep nets. Okay. Now, just to illustrate the limitations of this regime, let's look at a concrete example. So this is a slightly outdated example, but the point that I want to make from this example is actually as salient as ever. So labeled faces, it used to be a gold standard data set for facial recognition. And it was 80% white and 80% male. And these biases, they propagate to even the most heavily engineered commercial models. So a couple of years ago, there was an influential project that many of you probably know about, Gender Shades, which showed that these models actually have widely disparate performance across different demographic groups. So here, at the risk of using a reduced binary notion of gender, if you look at the performances of these commercial classifiers, then you can see that they all do pretty well on these green demographic groups and almost perfectly on pale male faces. But then for females with darker skin tones, they do rather poorly on. And this gap in performance can be as large as 30 to 35% in accuracy. Now, what's really worth noting here is that the most disadvantaged group of people was determined by an intersection of skin tone and gender. And although this particular experiment chose to look at two demographic characteristics, this is true in general. The most disadvantaged subpopulations, they're often determined by an intersection of multiple demographic characteristics. And this is what makes this problem particularly challenging, because even defining these disadvantaged subgroups that you want to protect against, it can be a pretty non-trivial task prior to having trained and deployed your model. So today, instead of simply optimizing the average case performance under the data generating distribution, we're now going to consider a whole bunch of different distributions in the set script P, and we're going to minimize the worst case loss under this region, under the set of distribution shifts. Okay. So this is called a distributionally robust optimization problem. And the rough idea here is that you want to learn models that instead of just doing well on average, right, in light of these biased data and whatnot, you want to do well almost all the time. Now, conceptually, the advantages of these types of approaches is really that it forces you to carefully think about what types of distribution shift you want to protect against. So since I first started working on these topics around 8-9 years ago, there's been an outburst of so-called robust or causally invariant procedures within ML. But a lot of these procedures are quite vague about exactly which type of distribution shift that they're trying to address. So here, this worst case region, it really defines the problem that you're trying to solve. And it's actually quite nice to be able to clearly specify exactly what kind of robustness that you're trying to build into your system, right? As opposed to, say, making up some algorithm, and then you search for a few data sets where your algorithm exhibits non-trivial behavior, and there's your next year's paper, which is still interesting, but it's very then hard to argue whether a particular distribution shift is relevant in your application or not. And this is, and in specifying these types of explicit distribution shifts, it's also the key to building better benchmarking, which is, of course, what allows the empirical field of ML to advance. All right, so the specific way we're going to do this today, it's going to look natural mathematically, but maybe realistically, from an application viewpoint, initially it's going to look somewhat contrived. But then later on, we're actually going to see that this is a relevant set of distribution shifts in a number of different applications. So the specific way that we're going to do this is by looking at distributions around the data generating distribution. We're going to look at all local perturbations. Okay. So to find this neighborhood around the data generating distribution, you of course need some notion of distance for probability measures. And we're going to use what's known as F divergences. Okay. So F divergences, they measure the distance between P and Q, two distributions, by measuring how much their likelihood ratio deviates from the value 1. Right? When P is equal to Q, the likelihood ratio is always going to be equal to 1. So now we want to measure how different the likelihood ratio is from the value 1. And the way you do this is by taking a convex function that looks like this with a minimum at 1, and you penalize deviations from the value 1 using this function. Okay? So the F divergence between Q and P is given by the expectation of this function F evaluated at the likelihood ratio. Now notice here that the curvature of this function, this F function, is what modulates how you measure distance. Right? So if the curvature is flat, this means that you're not penalizing deviations from the value 1 very much. So your F divergence value is in turn going to be small. Okay? Low curvature means smaller F divergence. All right. So now the finite sample version of our distribution robust problem is simply going to be an F divergence ball around the empirical distribution. Right? So here we're going to use rho as the radius of this ball, which is of course going to denote the level of robustness. So here we're going to end up solving this worst case optimization problem over distributions around the empirical distribution. And intuitively, what this minimax problem tries to do is it upweights harder examples in your training set, right? Those that suffer a high loss under the current model. Okay, so here's the DRO problem again. And I'm actually not going to go that deep into optimization today, but I do want to mention that you can solve this minimax problem efficiently by using a number of different approaches. You can easily imagine running gradient descent or accelerated gradient descent type procedures on this inner worst case objective. Or you can take the dual of the inner maximization problem, out pops a minimization problem. You combine it with this outer min over models. So you get one big minimization problem, which you can then, say, apply SGD on. Or you can also try to come up with stochastic gradient based schemes for solving this minimax problem. Okay. The high level takeaway here is that you can train models in this robust fashion at a fairly scalable manner. All right. So the rest of the talk, I'm going to try to first understand what this DRO formulation actually does. Okay. In particular, I'm going to prove that distributional robustness is actually equivalent to optimizing the worst case subpopulation performance. And then I'm going to show a convergence result that shows that robustness, it doesn't come for free. And you actually pay for it in terms of sample complexity. And finally, if time permits, I'm going to go over an extension of our DRO formulation that considers covariate shifts only over a subset of the features. So it's a less conservative formulation. So I think this is actually a good place to take a step back and discuss what's notably missing from this outline. So one notable open problem is how to scale these methods to deep nets. Right, so as you can see now, our procedure, it simply reweights the data in some adaptive fashion. So this worst case optimization viewpoint, it's not really useful for over-parameterized models that can fit the entire training set, right? So deep nets, after you train for a while, it essentially achieves zero loss on each and every one of the training points. And there's recently been some interesting proposals towards early stopping before you can achieve zero error on the entire training set, but there's certainly a lot of remaining questions here, and I'm happy to talk about them offline if you're interested. Okay, so now I'm going to show that our DRO formulation optimizes a notion of a worst case subpopulation performance. But before I go into the details of this, let me actually discuss a really simple idea towards potentially improving subpopulation performance. Let me actually briefly explain why this falls short of what you'd want in practice and how DRO can address this particular issue. So you can easily think about coming up with some predefined set of demographic groups that you want good performance over. And then maybe you can train a model separately on each group, or you can train a single model to work well with respect to the worst off group. They're all pretty natural ideas, but they actually have a number of key limitations in practice. So there's actually a number of applications, like, say, speech recognition, where this demographic information is simply unavailable because it's not appropriate to collect them. For example, Siri doesn't know that I grew up in Korea, and as a result might have this minority accent, which may affect its performances. And in insurance, of course, in the US, it's actually even illegal to use some of these demographic variables. And the biggest problem with these predefined demographic groups is that these are actually quite difficult to define a priori to actually having trained and deployed your model, right? A lot of these key variables, they comprise a continuous spectrum, and it's somewhat unclear how to discretize them. So as you saw in the facial recognition problem, skin tone was a continuous variable, right? And on top of this, as we again saw in that problem, the most disadvantaged groups are often determined in an intersectional fashion by a combination of multiple demographic variables, like your race, gender, income, age, and in medical scenarios, your genetic information as well. And once you start accounting for all of these different variables, you're going to soon end up with an exponential number of subgroups, rendering either of these approaches both statistically and computationally difficult. And so, for example, in natural language processing, performance of these models on, say, tasks like summarization, they, of course, vary across different demographic characteristics, but also they vary across document-specific traits, like how abstract the document is, or how much concept is distilled in it, or how dispersed the information is, and stuff like that. And it's going to be very difficult to define these subgroups over these concepts. Okay, so today what we're going to do is we're going to consider an infinite number of subpopulations. We're going to see how our robust procedure can automatically identify the worst of subpopulation and optimize performance on them. Okay, so here's our DRO formulation again, where we're taking this worst case objective over a distribution Q that are F divergence rho away from the data generating distribution P observation. Right? Now, intuitively, you can think of these distributions Q as subpopulations of the data. And I'm going to start by making concrete the sense in which this level of robustness rho, how this modulates the size of the worst case minority group that you want to optimize performance against. Okay. And again, DRO, it doesn't require specific attributes, and it can automatically consider an infinite number of subpopulations. All right. So let me first define what I actually mean by a subpopulation. So today I'm going to say that a distribution Q is a subpopulation of the underlying data generating distribution P if it's a mixture component of this distribution, right? So formally, this means that there exists a demographic proportion, small a, which is a number between 0 and 1, and another distribution q prime, such that if you mix q and q prime together according to this demographic proportion, then you recover the data generating distribution. Pictorially, this purple curve, it's a subpopulation in the sense that if you mix the gray curve with the purple curve according to the demographic proportion equal to 20%, then you exactly recover this black curve, which is the underlying data generating distribution. Of course, given a base distribution, there's an infinite number of different subpopulations that you can think about. So here is another example, another one, and another one. Is that my last one? Yep, cool. Now, to simplify notation, I'm going to say that a distribution, a subpopulation Q, is larger than some number alpha, which is a number between 0 and 1, say 20%, if the demographic proportion corresponding to this subpopulation is larger than this level of alpha. So what this notation means, Q larger than alpha, say 20%, this means that the subpopulation Q is represented at least 20% of the time in my training data. That's what this notation is going to mean. Given this notation, we can now write down the worst case loss over all subpopulations larger than this fixed level alpha, right? That's what this quantity is. This is a notion of a worst case subpopulation performance. Now, as we're going to see in a bit, it can actually be somewhat restricting to train models only against subpopulations that are larger than some fixed level. So to get around this, you can actually define a more general notion of a worst case subpopulation performance, one that can incorporate even arbitrarily small subpopulations. So instead of this fixed lower bound on the demographic proportion, let's now consider a random minority proportion, capital A, and let's say that this follows some distribution P sub A. Okay. So given this, now we can again define the worst case loss over all subpopulations larger than this random minority proportion, capital A, and then I can just take the average over capital A. Now, I don't really know how to model this distribution P sub A, so we can also, again, think about taking some set of distributions and taking the worst case over them, okay? So this now gives us a very general notion of a worst case subpopulation performance. Now, why did I do this, right? This looks like a pretty wacky object, this very general notion of a worst case subpopulation performance. So why this particular form? So that's what this next lemma shows. So what this next lemma shows is that any distributionally robust optimization problem is equivalent to optimizing the worst case subpopulation performance in this general sense. Okay. So for any DRO problem under regularity conditions, you can come up with a distribution over these random minority proportions such that this equivalence holds. Okay. So now we're going to operationalize this insight. And we're going to connect this worst case subpopulation interpretation back to particular F divergences. Okay. And in particular, we're going to show that our robust formulation with F divergences, it allows protecting against subpopulations that are sometimes arbitrarily small. So here's our distributionally robust formulation over F divergence balls. And here I'm going to use F divergences that look like power functions. Okay. So K here is denoting the curvature of this function F. Right. So if K is small, K is near 1, then this means that this F function is very flat. So that means that the F divergence is small, which means that my worst case region is big. So I'm being very conservative. Okay. So K small means you're being very robust or conservative. Okay. So again, what this lemma shows is that for these power divergences, there exists some particular set of distributions on the random minority proportion such that this equivalence holds. But this set down here, it looks really horrible, right? So oops, you don't actually have to know anything about that set. What really matters is that this is just a set of distributions such that the random minority proportion is, in some probabilistic sense, lower bounded by this number alpha. And alpha here is the size of the subpopulation that you want to guarantee good performance over. And we have an explicit formula linking rho, the level of robustness, to alpha. So as you become more robust, as rho grows, alpha becomes smaller, somewhat naturally. So now, armed with this interpretation, this equivalence now gives us a way to interpret the hyperparameters of this robust formulation, right? K and rho. From this equivalence, right, you can see that when rho is small, equivalently when alpha is large, when alpha is large and when K is large, this means that you're not being very robust. Right? You only care about large enough subpopulations. And then as K becomes smaller, as alpha becomes smaller, or equivalently, as rho grows, you're becoming more robust, meaning you care about smaller minority groups. Okay. Now, selecting these hyperparameters, they're actually somewhat non-trivial in practice. So in our paper, we actually propose a couple of different heuristics for choosing these values based on cross-validation. So now that we obtained this nice interpretation for our distribution robust objective as a notion of a worst-case subpopulation performance, we're going to analyze its statistical properties. And in particular, we're going to study the extent to which we can optimize the worst-case subpopulation performance based on a finite sample of the data. Right? So we're going to take a look at a particular viewpoint today, which is known as the Minimax Principle in statistics. So here we're going to consider a statistical modeler or a machine learning engineer, let's say myself, who's trying to come up with a good procedure theta hat, an algorithm. Right? And nature is going to select the data generating distribution P observation. And from this distribution, n IID data points are going to be generated. And the procedure theta hat that I designed as the machine learning engineer, it's going to take these n data points, right? And it's going to spit out some model. Now, a relevant notion of performance in this setting is to consider, of course, the distributionally robust objective, or equivalently the worst case subpopulation performance, suffered under the procedure theta hat. Right? So I'm going to look at the worst case subpopulation performance, the distribution robust objective, suffered under my procedure theta hat. Right? And I'm going to compare this with the best thing that I could have ever done in the limit of infinite data. Right? The term at the right end in this blue box. So this thing now is my optimality gap. And since I don't know what nature is going to choose as my data generating distribution, I'm just going to take this max over all data generating distributions such that my data points are bounded. Now, my job as the statistical modeler, as the machine learning engineer, is to minimize this excess risk, right? So this entire quantity is called the minimax risk of learning. And it's actually a fundamental quantity in statistics and machine learning because it quantifies the extent to which you can optimize the worst case subpopulation performance by just looking at n data points. Okay. Okay, so our main theoretical result today, I promise I'm going to show you some interesting experiments later. So the main theoretical result today is going to say that this minimax risk, it goes to 0 at this very particular rate of emergence. And this is actually a pretty interesting non-standard rate of emergence. So when the curvature of the F divergence, K, is greater than 2, so this means that you're not being very robust, right? Or equivalently, you only care about large enough subpopulations. So when this is the case, then you get the usual rate of convergence, 1 over square root of n. But then as you become more robust, as K becomes smaller, right, as you care more about small subpopulations, you suffer this slowdown in your convergence rate. That's what the second rate says, okay? And the way we show this result is by taking a two-pronged approach, where first we substantiate this result in the sense that I'm going to come up with a procedure that actually achieves this rate of convergence. And then we're going to show a fundamental hardness result, which says that no procedure that I could have come up with as the machine learning engineer can actually do better than this error rate. Okay. So this fundamental hardness result is going to show that this slower non-parametric rate of convergence is actually necessary and unavoidable if you want to optimize performance against small subpopulations. Okay. So again, these two prongs, this is what allows us to quantify this rate at which we can optimize the distribution robust objective by just looking at a finite number of data points. All right, so now let's empirically verify the sense in which DRO improves subpopulation performance. So first, I'm going to look at dogs, and I'm going to classify images of dogs to their dog breeds. In this example, there's going to be 120 different dog breeds, 120 different classes. And this is going to be an interesting setting because there's actually going to be no underrepresentation bias here. So for each class, there's going to be the exact same number of images in the training set. Okay? And even in this example where all of these subgroups are evenly represented, we're going to see how these fundamentally difficult classes actually naturally emerge. So I'm going to use histogram kernels on SIFT features, very simple features, to generate my x's. And I'm just going to fit a multi-class logistic regression loss, right? So this is just a linear problem, very simple setting. Now, if you train an average case ERM model and look at the class-wise accuracies across these dog breeds, then you can see that there's these certain dogs that you excel at classifying, right? Your error rates are pretty low. There's this humongous gap between different classes, different dog breeds. So if you look to the left of this plot, you can see that there's certain dogs that you almost always get incorrectly, right? Your error rate is very close to 100%. So here, there's a really big gap in performance as large as 70% in accuracy, even when you have no underrepresentation bias. So let's see what our DRO procedure does in the setting. Right? So I'm just going to set k equals to 2 for simplicity. And in the y-axis here, I'm looking at the accuracy across 120 different dog breeds. And I'm going to take the standard deviation of this 120 different 120 dimensional vector. Okay. And on the x-axis, I'm plotting this with respect to the subpopulation size. So as you go to the right of this plot, you're becoming more robust. You care about smaller subpopulations. Okay. And what you see is that as you become more robust, as alpha becomes smaller, you actually perform more uniformly across dog breeds. And this is quite interesting given that our procedure, it doesn't even explicitly train for this at all. And to see this more clearly, let's now look at this plot where I'm taking 6 different models. The first model is the average case ERM model, and then the rest of them are DRO models with varying levels of subpopulation size, with varying levels of robustness. Okay? And for all of these models, I'm taking the X classes that they do the worst on, and I'm going to compute the accuracy of these models on these X classes, where X is the value that varies on the horizontal axis. Okay, so when X is small, this means that we're looking at the worst case performance, and as X becomes larger, we're approaching the average case. Right, so this is a slightly non-standard plot, so it takes a little bit of time to take in. So the left-hand side of this plot is measuring the tail performance of each of these models. And you can see that the ERM model, as we saw before, it has a really poor tail performance. Its error rate is very close to 1. And then as we become more robust, the tail performance actually improves quite dramatically by up to something like 20% in accuracy, which is actually a pretty big gain considering the fact that we're using the exact same features here. So what we see is that by virtue of improving the subpopulation performance, we actually even do better on average compared to the ERM. So there is a non-trivial regularization effect going on here. And we've actually studied this regularization effect of DRO in a number of previous works. And I'd be happy to talk about it more offline if any of you are interested. Okay, so in this example, it's probably the case that the rudimentary kernel features I'm using, it might not be good for particular classes, right? But it's still very interesting that you can improve performance this much by just adaptively reweighting your data. All right. So far, we assumed that you train a model once and then you deploy it, right? Now, let's consider a slightly more realistic setting where we deploy a model and then users interact with this model over time. And here, let's say that every once in a while, we're going to refit the model based on the current user data, right? So in this repeated loss minimization setting, if you have a speech recognition system that, say, consistently underperforms on a particular demographic group, the members of this group are more likely to stop using the service, thereby no longer providing data, right? So this will further exacerbate the system's ability to optimize performance on this disadvantaged group. So now you see this negative feedback loop emerging through time. Okay, so again, the performance on minority groups, they can get worse over time as users begin to leave the system. So to pictorially see this degradation in minority performance over time, here I have a toy example. So here I have two different unseen latent demographic groups, right? And the goal here is to classify each dot as each person as a plus or a minus, okay? And let's say that we have this blue line, a model that works almost equally well on both of these groups. Now, for some reason, if this model worked ever so slightly worse on the right group, right, then people in the right-hand side group are going to start to disproportionately leave the system. So if you refit the model after a little bit of time passes, then it's going to be slightly tilted to work better on the majority left-hand side group. And as time goes on, this trend is going to continue, and you're going to be left with a model that entirely tailors to the majority group. So this is what happens over time. Okay. So in this toy example, if you look at the accuracy on the minority group, the right-hand side group, so here I'm looking at accuracy, so higher is better. Okay. So what we see is that the average KCRM model's performance, it degrades significantly over time. On the other end, if you use our worst case subpopulation procedure, the DRO procedure, then you see that it's actually able to provide a uniform level of performance even through time on this unseen demographic group. And you can actually quantify this, and you can show that under certain user retention dynamics, the average KCRM procedure, it's unstable in the sense that even initially small disparities can amplify through time. On the other hand, if you control for the worst case subpopulation loss using the distribution robust approach, then you're actually able to control the minority proportions over time, and thereby you're actually able to guarantee a level of performance over these minority groups, even in this repeated loss minimization setting. Now, this toy example setting is of course very contrived. So let's actually concretely see this phenomenon on a slightly more realistic setting. So here we're going to look at an autocomplete system, where as you're typing a sentence from the left to the right, we want to predict the next word. Okay. And the problem here is that text from minority groups, they don't get surfaced as often. So this leads to biases in performance. So let's say that you're a Twitter user using African-American vernacular. And if the model was trained on a data set that was largely dominated with standard American English, then your sentences may never get auto-completed. Okay? So in this setting, we have the retention feedback loop as before, where if the system doesn't work well for African-American vernacular users, then people in this group might start to leave the system, and the remaining users might incur an even higher loss at a future time step. So we have this natural feedback loop, and in this feedback loop, everything else we can measure. We can train the model, we can evaluate its prediction error. But what we don't know how to relate is the prediction error to the retention rate, right? So we designed an experiment where we can actually do this on Mechanical Turk. So here we took a corpus of sentences from Twitter, and each of these sentences have been classified as being either in the African-American English group or the standard American English group by Blodgett et al. Okay. I'm not a big fan of this nomenclature, but I'm just going to use it following the set of authors. So here we trained an autocomplete system on different data sets formed with different mixtures of these two groups. Okay. So I take different mixtures. I have a bunch of different data sets. For each of them, I train a model. Now, at test time, I'm going to give a sentence from either of these groups, out of sample, of course, to a Mechanical Turker, to a human. And we're going to ask this Turker to type this sentence in real time. Okay. And as this Turker types, our model is going to try to autocomplete their sentence, and this person is going to see this. And when they're done typing, we're going to ask this person whether they're satisfied using the service or whether they want to stop using it. Right? So if you're using a model that was trained mostly on standard American English, then the system will perform poorly on African American English users. So by looking at our survey, we can simulate the dynamics of user retention through time. So here we see exactly the same dynamics as we did before on the toy example. So if you use a standard average case ERM procedure, then people in the African American English group who initially got slightly lower accuracy, they start to drop out of this autocomplete service over time. So in the future, they receive an even worse performance. On the other hand, our DRO procedure, the worst case subpopulation procedure, it's able to control the demographic proportion of this unseen minority group. So it's thereby able to guarantee a level of performance on these minority groups even through time. So even in this repeated loss minorization setting, our worst case subpopulation procedure, it can provide this uniform level of performance over these arbitrary minority groups. All right, so until now, we considered distribution shifts in the joint distribution of the covariate label vector x comma y, right? And this is appropriate if there are, say, unmeasured confounders that affect both the features and the label simultaneously. For example, you might have unmodeled temporal effects yielding non-stationary behavior. You often have unobserved demographics that substantially shift across space and time. And of course, a lot of these NLP tasks, they have annotator artifacts that a lot of these models might be overfitting to. So this is all fine and good, right? But protecting over shifts in the joint distribution, it can be overly conservative if all you care about is distribution shift in a subset of the covariates, right? If you only want to guarantee uniform performance only over a small set of the features, then this joint DRO may not be the right thing to do. For example, in a medical diagnosis setting, you might not care how long my fingernails are, right? So maybe you don't want to guarantee uniform performance with respect to this rather random feature. So here we're going to talk about an extension of our discussion so far to this covariate shift setting, where the probability of y given x is fixed, and we're interested in distribution shifts only in the marginal distribution of x. And again, this is equivalent to considering subpopulations of the marginal distribution, right, on this covariate vector. And more generally, our approach actually can handle any protected set of attributes. Let's call it z here, right? But for notational simplicity, I'm just going to take z equals to x, at least for the sake of this talk. Okay. But more generally, you can define z to be, say, the abstractiveness of the NLP task, or you can define it using metadata on the spatiotemporal information about the image in a computer vision setting or something like that. All right. So again, we can consider distribution shifts with respect to these marginal distributions, right, over the covariate vector. And here we can again write down the worst case loss over these distribution shifts. Okay. So here you can see that the worst case is now taken over the conditional risk, this middle quantity. Okay. So this is the quantity that averages the loss conditioned on the covariates. And this is what we're going to call LC. Okay. And just as a side comment, if you opt for the more general version, you can replace the conditioning conditioned on X with conditioned on Z, right? So it's as easy as that. All right, now the key technical difficulty in the setting is that this conditional risk, it's never observed, right? And it's actually really difficult to estimate uniformly over theta and X because given any feature vector X, we only have a very limited number of replicate labels. For example, in most prediction scenarios, you just have one label or outcome per covariate vector. So now we have this really interesting technical problem where we want to solve this minimax problem, but we don't even observe the conditional risk. And to circumvent this difficulty, we're going to use a dual reformulation. Right? So let's go back to our DRO formulation with f divergences using these power functions. So again, k is the curvature of this function f. So it modulates conservatism. Lower the k, the more conservative you are, right? Now, what this lemma says is that this distribution robust objective or equivalently the worst case subpopulation performance, it has this dual over this threshold eta. Okay, and this dual problem, it illustrates that this worst case loss, it only cares about people with bad enough conditional risks, right? So you threshold at this level eta. Now, why did we derive this dual form, right? So if you take a look at this inner expectation term, this LK star norm, so that's what I've written down below this blue box, right? Now I'm going to apply the variational representation of the LK star norm here, also called the dual norm, and you can represent this as a supremum over functions of x that has bounded kth order moments. Okay. The nice thing about this variational representation is that there's no dependence on the conditional risk on this right-hand side. This is fantastic, right? We never observe the conditional risk, and this is very hard to estimate uniformly over theta and x because we almost always don't have these replicate labels. So we get over this by taking this variational form. Now, the problem now is that it's still very hard to estimate the supremum over the class of all positive functions with bounded moments. It's just too large a set, right, for us to be able to estimate using a finite number of samples. So what we're going to do in this next lemma is we're going to assume that our conditional risks and the losses are smooth in the daytime. Okay, and this actually allows us to restrict this function class in the variational representation. So if we assume that the conditional risk and the loss is Lipschitz with respect to the data, then you can show that this variational representation, right, in the previous slide, it can be restricted to appropriately smooth functions. And as you can see, I'm hiding a bunch of things in this lemma box, so it's not very rigorous, but the high-level idea is still crisp here. And you can, of course, read our paper for the precise formulation, or I'm happy to chat more after the talk. All right, so again, the key here is that now we've replaced the conditional risk that we don't observe with losses which we do observe. So we're going to use this to derive a procedure that trains models against covariate shifts, which is what we're going to call the marginal error formulation. So summarizing everything we've done so far, we had the distribution robust objective over covariate shifts, right? It involved this conditional risk that we don't observe. So we reformulated it into a dual form, and then we wrote down the variational representation, and we restricted the set of functions in that variational representation. Okay. So now we can approximate this using finite number of samples and then train models with respect to this. So in the lower empirical problem, we have this inner supremum that looks rather horrendous. So in our paper, we actually give a dual procedure which can be solved efficiently. Okay. And also in our paper, we give various concentration guarantees for this procedure, but without really getting into these theoretical results, let's see if our procedure is actually doing anything meaningful in a practical fashion. So here, let's look at the marginal error procedure on a real data set. So here we have a simple semantic similarity prediction task. We're given two word vectors. We're going to use glove embeddings. We want to predict the semantic similarity. Okay. And the interesting thing about this data set is that it's a very rare example where we actually have a few replicate labels. So here, per pair of words, in this data, we have 13 different human labels for their level of similarity. So at test time, we can use these replicate labels to approximate the conditional loss, the conditional risk. Okay, so this is what allows us to measure the test time worst case subpopulation performance of various different models. Now at training time, we're just going to fix alpha train equals to 30%, meaning we only care about minority groups that are at least as large as 30% of the training data. But at test time, we're going to test all of these models over many, many different values of alpha. Because in practice, you never know the true level. Okay. Again, here we're evaluating all of these models under this worst case subpopulation performance over covariate shifts, over marginal distribution shifts. Right? So on the y-axis here, we have this quantity, and on the x-axis, I'm varying the minority group size at test time. So at the rightmost point of this plot, this is the average case performance. And you can see that joint DRO, the original approach that we considered, and ERM, the average case approach, and marginal DRO, our new approach, all of them perform fairly similarly. They all achieve pretty good average case performance. But then the average case ERM solution, if you go to the leftmost point of this plot, you can see that around 5% of the test set, it essentially reduces to a random guess. So it performs really terribly. Now, on the other hand, the joint DRO approaches, and much more so the marginal DRO approach, by virtue of not being as conservative, you can see that all of these approaches, they reduce this tail error in a substantive and significant fashion. Okay. And you also see this pretty big gap between marginal DRO and joint DRO. And the key difference here is the level of conservatism. All right, so before I end, I just want to mention briefly an extension of this covariate shift setting that we've studied so far. So the marginal DRO setting, again, it assumes that the conditional distribution of y given x is fixed, right? And this was the key difference to the joint DRO setting. But what if you think that there's a little amount of confounding, right? Meaning that you're worried about maybe small shifts in y given x. So you care about big shifts in x, but then small shifts in y given x. So if you're willing to postulate a bound on the magnitude of the confounder, then it turns out you can use a variant of our marginal DRO formulation. So in particular, if you're willing to assume that there's some unobserved confounder C such that y given x and c is fixed, and that the conditional risk given x and the conditional risk given x and c are uniformly closed, then you can formulate a variant of our procedure. And this procedure actually often outperforms joint DRO, again, by virtue of being less conservative. And our formulation here is actually quite nice in that it smoothly interpolates between marginal DRO and joint DRO. And of course, I don't really have the time to go into the details here, but I'm happy to chat about this extension offline if any of you are interested. All right, so just to wrap up, we discussed how DRO is equivalent to optimizing the worst case subpopulation performance. And then we studied the trade-off between robustness and convergence rates. And we also saw how this distributional robustness notion allows us to train models that can maintain a stable level of performance over time as systems interact with the user. Now, I want to end by saying that there's actually a lot of really interesting connections with distributional robustness and causality. And I hope some of the language I've been using so far has been somewhat evocative of this connection. So a distributionally robust model that's invariant to particular interventions, it's also the goal of causal prediction. And I think this is actually a very interesting and rich research direction in the sense that you can exploit the particular structure of the problem. You can write down a particular DAG for the problem and use this structure to formulate, say, the worst case region for a distribution robust formulation. And the connection also goes the other way. You can use notions of distributional robustness to ascertain the validity of causal findings under violations of key assumptions like the presence of unobserved confounders or unanticipated covariate shifts. All right, so I think I'm out of time, so I'll end here. Thanks a lot for your attention, and I'm happy to stick around if you have any questions.
Maybe like one question I have is, like for the F divergences, like you showed this, like I can say negative results for certain F divergences, because like you relate it to the worst case scenario. What type of F divergence can I put there and get a positive result?
Sorry, what do you mean by a positive result?
In the sense that we can say it's much better, like getting like distributionally robust is much easier than like getting basically an adversarial robust. So like, yeah, like maybe I want to like have families of problems under for which, for some definition of for some variant of this distributional robust under some F divergence, I can actually get much better results than.
So I think the key difference here is that the distribution shift that you're trying to address is different. So the typical adversarial attack regime studies a very particular security-motivated set of distribution shifts, right? And you can try to write it down in a DRO type fashion, but the worst-case region is going to look substantially different than these F divergences, in the sense that these F divergences, the key limitation is that the distribution shift Q, it needs to have the same support as the data generating distribution. Whereas, say, in a typical adversarial attack setting, you are essentially going outside the support of the data generating process. So there's a lot of these types of high-dimensional problems where the exact type of distribution shift actually matters a lot. And I don't think we understand these trade-offs or differences very well.
Okay. Thank you. Interesting talk.
Thanks.
Yeah, I guess we're running out of time. So let's thank the speaker. Very nice talk. Thank you.